is we are going to move from lines to quadratic functions. So we're going to go from linear functions where we have variables raised to the first power to quadratic functions where our input is raised to the second power. If you have a quadratic equation, that's an equation that can be written in the form ax squared plus bx plus c equals 0, okay, where a, b, and c are real numbers and a is not 0. Now, why do we say a is not 0? Well, if a was 0, then that term would be missing and we would be back down to a linear equation. Okay, so we're going to have something non-zero multiplied by the x squared term. If you want to talk about a quadratic function, which we will, instead of just a quadratic equation, it's just where you have an f of x is equal to ax squared plus bx plus c. So for example, if you had something like f of x is equal to 3x squared plus 6x plus 2, we would call this a quadratic function. How would I find, say, f of 2? What would I do? Plug 2 in wherever I see an x, just like I would for any function. So I would have 3 times 2 squared plus 6 times 2 plus 2, or that's 3 times 4 is 12, plus 12 is 24, plus 2 is 26. So 1 point on that graph would be the point 2, 26. This is a quadratic function. This, on the other hand, is linear. So we have linear versus quadratic. Okay, so in the next 2 or 3 sections, we're going to be talking primarily about quadratic functions and quadratic equations. Specifically in section 7.4, we're going to start talking about how to solve quadratic equations. One of the things that we need to be able to do is find where a graph crosses the x-axis, or in other words, find the zeros of a function. The zeros of any function are where they're the x-coordinates of the x-intercepts, or in other words, they're the solutions that you would get by setting the function equal to 0. So setting and solving quadratic equations has some graphical ramifications as well. But first things first, before we get to graphing quadratic functions, we want to solve a quadratic equation. Couple of ways that we should have done somewhere before, but we won't concentrate on these, but we should have seen and perhaps be able to do solving by factoring and then also by the principle of square roots. Don't stress, let's just look and see what that means. If you're asked to solve a quadratic equation by factoring, what that means is we try to get everything on one side. Okay, so if I wanted all my terms on one side here, I'm going to subtract 3 from both sides and rewrite this as 2x squared minus x minus 3 is equal to 0. When you're solving by factoring, what we're actually using is the principle of zero products. What that means is if I can rewrite this left-hand side as the product of 2 factors. If I have something times something else is equal to 0, the principle of zero products means that one or the other of those 2 things has to be 0. You can't multiply 2 non-zero numbers together and get 0. So what we're going to try to do is come up with 2 binomials such that when I multiply them together, I get 2x squared minus x minus 3. So how do we do that? Well, we divide this first term up where the first 2 terms here multiply together to give me a 2x squared. So I'm going to have, I don't have very many choices for that one. I'm going to use 2x and 1x. Okay. Now, if that had been a bigger number like 72x squared or 64x squared, there'd be a lot more choices for those first two. But your first two terms in your binomial factors multiply together to give you your leading term in your quadratic equation. Now, the last two terms need to multiply together to give me the -3. So once again, I don't really have many choices. I could go with a 1 and a 3 here. But they do need to multiply together to give me a -3. So then I'd have to go, well, should I do a -3 and a +1, or would it be a -1 and a +3? But then what do I have to do? Well, I have to ask myself, do these multiply together to give me this? Well, the first term and the last term's good. But if I multiply the outer term here and then the inner term, I would have -6x plus 1x is a -5x. I need just a -1x. So that one doesn't work. What about this one? Well, my first two terms, if I FOILed that out, I would have a 2x squared. And then when I multiplied my outer terms and my inner terms together, I would have plus 6x minus 1x is plus 5x. So that also doesn't work. So I go back and say, okay, well, I know those first terms need to be a 2x and a 1x. And I didn't really have any choices much for the 3. It has to be either 3 and 1 or 1 and 3 if we're going to factor it. So the other option is, instead of putting the 3 in a set of parentheses with the 1x, let's put it over here with the 2. So I'm going to switch the order of the 3 and the 1. And I'm going to say I'm going to try a -3 here and a +1 there. If I multiply that out, that's 2x squared plus 2x minus 3x is indeed minus x. So that part's good. And then we have -3 times 1 is -3. So this part is equal to what we started with, and we're going to set that equal to 0. But already, can you kind of see some of the drawbacks to the factoring method? It's great when you can see how to factor it pretty quickly, but even for some relatively small numbers, pardon me, if you're using a guess and check type situation, it can get to be kind of time consuming. And especially if the numbers start getting bigger and bigger here, and the number of different possible combinations gets bigger, then there's lots more options to check. Once we do have this left-hand side as the product of two factors, what we do is say, okay, well, if this times this is equal to 0, using the principle of zero products, we would know that either the first term is equal to 0 or the second term is equal to 0. Solve both of these and we would get x plus 1 equals 0 is just x equals 0 minus 1, which is -1. 2x minus 3 equals 0 would give us 2x equals 3, or x is 3/2. So our solutions to this equation would be the set containing 3/2 and -1. Now remember, when we had linear equations, typically we ended up with one solution. Now we may end up with two. Okay, and in fact we may end up with two real solutions, or we could end up with the same solution twice, or a variety of different options. I know you've done some of these factoring processes because we had some back when we solved rational equations, but that is one way to solve a quadratic equation. is by factoring. It's great when it works quickly and you can find combinations that give you your original. When you get bigger and bigger numbers, it's not quite so easy. So in this section, what we're going to talk about is other methods as well of solving a quadratic. Any questions at this point? All right. We also sometimes use what we call the principle of square roots. That's particularly useful when you just have a quadratic term and a constant term. When we have something where we have an ax squared and then a constant equals 0, to use the principle of square roots, we may move the constant to the other side and isolate the squared term. So when I isolate the squared term, I divide both sides by 2, and I'd get x squared is equal to 5. Now, if x squared is equal to 5, we want all the solutions, so we'd take the plus or minus square root of 5. Now, when you're using the principle of square roots, what we know is that if x squared is equal to a constant, that means that x is either the square root of that constant or the negative square root of that constant, which is why I have the plus or minus square root out front. And that's also a great way to solve a quadratic equation if it's set up in that form. So what if we had, like, let's say 4x squared equals 81. To solve that, I would divide both sides by 4 and get x squared equals 81 over 4. So x would be either plus or minus the square root of 81 over 4. Now, if I then enter those two numbers into my MyMathLab answers, they're probably going to call it, come back and say, well, that's equivalent to the right answer, but it's not simplified. How could you simplify the square root of 81 over 4? Well, what's the square root of 81? 9, and the square root of 4 is 2. So rather than leaving it as the square root of 81 over 4, we would need to rewrite it as the square root of 9 halves. Is everybody still okay? Oh, did I say square root? I'm sorry, it's just 9 halves. Yeah, we have it written right. We already got rid of the square root. All right, so those are great ways to solve quadratic equations when they work. The problem is sometimes it's a little bit more involved than that. So what we're going to look at next is two methods that always work. Okay? For example, if I asked you to find the zeros of this function. Now remember, find the zeros of this function means set the function equal to 0. Okay, because remember, the zeros are actually the x-coordinates of the x-intercepts of your graph. We're not quite to the graphing part yet, but if we want to find the zeros, we would want to set that function equal to 0 and solve. Oh, if we tried to factor that, we just can't. I mean, we would have an x and an x, but 10 could either be 10 and 1 or 5 and 2. And we're not going to be able to get there from here. Okay? And since I have that middle term, just getting quickly to your answer by using the principle of square roots may be a little bit more involved as well. The method of completing the square always works. There's a lot to it, but it does always work. So that's what we're going to start with. So first things first, to complete the square, move the constant to one side by itself. So I'm going to rewrite this as x squared minus 6x is equal to 10. Okay, so let me just tell you kind of where we're going. What we're going to try to do is we're going to try to make what's on the left here a perfect square so that we can use the square root principle. But we're going to have to do some finagling first. Okay. Once we moved the constant to one side, if the coefficient of x is not 1, divide both sides by that coefficient. Okay, now in this case, remember the coefficient, I should have said coefficient of x squared, sorry. The coefficient of x squared here is the number that's being multiplied by x squared, and it is a 1. But it is the coefficient of x squared. If it's not 1, divide everything by it. We'll do one here in a minute where we would have to do that. But in this case, we don't. Okay. What I want is I want to add a number here to the left-hand side so that this becomes a perfect square. So just really quickly, what we're going to do is we're going to take like an x minus a times an x minus a. That's what we're trying to get on the left-hand side. Okay, that's x minus a quantity squared. If you multiplied that out, that would be x squared minus 2ax plus a squared. We're trying to figure out what this term needs to be to make that a perfect square. So what we do is we recognize the fact that this middle term is 2ax. So if in this case negative 6x is 2ax, cancel the x's, then that would mean that a is negative 3. That's what we're going to square and add to both sides. You don't have to go through this part every single time. To make this a perfect square, what we're going to do is we're going to take half the coefficient of x, square it, and add it to both sides. Okay, so the coefficient of x here is negative 6. Half of that is negative 3. So we are going to square negative 3 and add it to both sides. Negative 3 squared is 9. Now remember, if I add something to one side, I have to add it to the other side so that I don't actually change the equation. We just are writing it in a different form. Okay. By taking half the coefficient of the linear term here, squaring it and adding it to both sides, we have made this guy a perfect square. So we're going to factor the left side into the perfect square. This guy is x minus 3 times x minus 3, or that is x minus 3 squared. And that, in this case, would equal 19. If you have taken half the coefficient of x, squared it, and added it to both sides, this guy will always factor into the first term is going to be the square root of this one. This is going to be the square root of that one, and whatever that sign is will go in the middle. So if that had been a plus, this would be a plus. And you look at that and go, well, I have succeeded in making it look, well, I'm not sure it's any better than what we started with. But what we know is that if we have just a variable expression squared here equal to a constant, we can use the square root principle that we just used up in this part. So if we have something squared equals 19, that means that that something is equal to either plus or minus the square root of 19. So after we factored the left-hand side into a perfect square, we're going to solve using the principle of square roots. When I took the square root here and got x minus 3 is either plus or minus the square root of 19, am I done? Not quite. I really was wanting to know what x is equal to. So I need to get the x alone on one side of the equation. So I do still need to add 3 to both sides, and that would give me x is equal to 3 plus or minus the square root of 19. So we do have two solutions here. The solutions are 3 plus the square root of 19 and 3 minus the square root of 19. Now in this particular problem, the square root of 19 won't simplify because it is a prime number, so I can't simplify that radical, and that would be as good as we can get. Now many times they will ask you to leave your answer exact, so we'd want to leave it in this form. They may also ask you to give them a decimal approximation, depending. Most of the time I will ask for exact, but if you did want a decimal approximation, we would have 3 plus the square root of 19 is approximately 7.36, depending on where they ask you to round it. 3 minus the square root of 19 would be about negative 1.36. Once again, I rounded to 2 decimal places. They may ask you to round to 3 or 4. Why would we ever do this? Well, it is the method, the first method, that always works to solve a quadratic equation. Okay? Whereas you could try to factor that all day today and part of tomorrow and you'd never get there. It does always work. It's a lot going on, but it works. Questions before we do another one of those? Yes. Excuse me? Oh. I was like, wait, did he go that bad? It is kind of long, isn't it? Oh, that's fine. But yeah, it does get a bit long. But never fear, we will maybe get a little bit shorter version of it here in a few minutes. Well, it's, some of them are... when you can use a factoring, like if you can factor it, definitely do that, because if you can see how to factor it, that's much quicker. But people have a surprising amount of difficulty factoring, especially on one like this, because you can't factor it. And so, yeah, I get what you're saying. All right, let's try one more though let's try another one of those, and then we will see what we could do in general if we really didn't want to complete the square. All right. So if we have 2x squared minus 1 equals 3x, and we want to solve by completing the square. First thing I need to do is I need to get my constant term alone on one side. So I'm actually going to move the 3x over here and the 1 over here. So I'm going to add 1 to both sides, and I'm going to subtract 3x from both sides. So I will have 2x squared minus 3x is equal to 1. Okay? So that was step 1. Move the constant to the side by itself. And I always put the constant on the right just for consistency's sake, but it doesn't really matter. Okay, that was the first thing we did. On one side. Okay, now in this one, the coefficient of x squared is not 1, so we are going to divide both sides by that number. So I'm going to divide everything in this equation by 2. So I will have x squared minus 3/2 x is equal to 1/2. Okay? So we're going to get some fractions going on here really quickly. I know. I think that's true for everybody. Now, what we're going to do, though, is the same process. We're going to take half the coefficient of x, square it, and add it to both sides. Okay, so I'm going to take half the coefficient of x, which was negative 3/2. Half of negative 3/2 is negative 3/4. We're going to square that. Yeah, I was just doing this over here on my scratch work. Okay, and you can do it in the middle, that's perfectly fine. But we're just going to take negative 3/4 squared and add it to both sides. That's 9/16. Because remember, when you take negative 3/4 and square it, you take negative 3/4 times negative 3/4, which is 9/16. Okay? All right, so we're adding that to both sides. Now, we will factor the left into a perfect square. And simplify the right. In other words, add those two numbers together if you haven't already. All right, by what we added to both sides, this side will factor into the square root of this is x. The square root of this is 3/4, and then whatever that sign is. If that's a plus, this would be a plus. Since this is a minus, this will be a minus. And it's that squared. And of course you can check yourself by multiplying it back out and making sure. But all right, so what's 1/2 plus 9/16? Well, my common denominator would be 16. 2 goes into 16 8 times. 8 times 1 is 8 plus 9. So that would be 17/16 is equal to x minus 3/4 all squared. Okay. Once we do this, we are going to extract the roots or use the square root principle and solve. So we would get x minus 3/4 is equal to plus or minus the square root of 17 over 16. So x is 3/4 plus or minus the square root of 17 over 16, which is 3/4 plus or minus the square root of 17 over the square root of 16, which is 4. So if you wanted to write those separately, we would have 3/4 plus the square root of 17 over 4 and 3/4 minus the square root of 17 over 4. And that's about as bad as they get on our completing the square. Now, we go, that's just, as Laura said, it's just getting a lot. I mean, that's a lot of stuff going on there. And so if we take, and normally I would go through the process, but I just looked at the time, and I don't want to spend all the time deriving this and not enough time working them. But if you take a standard, just arbitrary quadratic equation, ax squared plus bx plus c equals 0, and you complete the square on that. This is why completing the square is so important for us to see, is if we complete the square on this equation, what we get is called the quadratic formula. Have you heard of the quadratic formula before, at least? Excellent. Where does that come from? It comes from completing the square on this equation, but it's usually a lot more user-friendly to use, right? So if you have an arbitrary quadratic equation, ax squared plus bx plus c, you can solve that using the quadratic formula by setting x equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So on that one that we just did, which is this one, we already solved it using the completing the square. If I wanted to use the quadratic formula on that same equation, rather than moving the constant to one side, we get everything on one side equal to 0. To use the quadratic formula, you need to set everything equal to 0. So we would have 2x squared minus 3x minus 1 equals 0. And we need to identify a, b, and c. A will always be the coefficient of the squared term. B will always be the coefficient of the linear term. In other words, the just x term. And c will always be your constant. So we would, no, a is the quadratic term. It's the leading coefficient, or it's the coefficient of your squared term. B is your linear term. But it's just the number parts of those. So a is just the coefficient, or the number in front of the x squared. B is the number being multiplied by the x, or the linear term, and c will be your constant term. So we will have x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. I can barely say the quadratic formula without saying it to the cadence of Pop Goes the Weasel. Did anybody ever sing that to you? I'm not going to sing that to y'all. But yeah, one way to remember it is sing it to Pop Goes the Weasel. x is equal, yeah, it's, I won't actually say it, but it's x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Yeah, I'm not going to sing it, but there you go. All right, so we have the negative of negative 3 is 3 plus or minus the square root of negative 3 squared is 9 minus 4 times 2 times negative 1 is plus 8, since it was a minus a negative, all over 4. So we have 3 plus or minus the square root of 17 over 4. Or that will be 3 plus the square root of 17 all over 4, or 3 minus the square root of 17 all over 4. Now, remember, we wrote this as separate fractions the first time we wrote it. Since we have a single denominator of 4, we could write that as 3 over 4 plus the square root of 17 over 4, and 3 over 4 minus the square root of 17 over 4, and those would be the same thing. But you got to admit, this is a lot quicker than going through this whole process. And it will always work on any quadratic equation. Okay? Yes. It is easier, but it does come from completing the square. So most of the time I won't ask you to do it a particular way, but I may ask you on some occasions to either complete the square or use the quadratic formula on it. But most of the time you'll get to pick your method. Okay. All right, so just to save time, because I want to make sure we get to a word problem example, let's go ahead and do this one. So it just says solve. If somebody just tells me to solve that quadratic equation and I don't see really quickly how to factor it, I'm going to use the quadratic formula on it. So in this case, we already have everything on one side. So I need to identify A. It's the coefficient of the squared term. B is the coefficient of the linear term. And C is the constant. So we would have x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. If you are in class right now, would you put a yes or here in the chat for me? All right, you guys just earned a point on your next quiz. Easiest point you ever earned, wasn't it? All right. Everybody does. We all want all the points we can get. All right, so let's simplify this. So we will have negative 5 plus or minus the square root of 5 squared is 25 minus 4 times 8 is 32 all over 2. Or that will be negative 5 plus or minus the square root of negative 7 over 2. Now, this would not be considered simplified. This was that self-study section. Remember, when you're taking the square root of a negative number, we factor the negative out from underneath the radical, and it comes out as the imaginary unit I. So that would be negative 5 plus or minus I square roots of 7 all over 2. So if you wanted to write that separately, if they ask you to write it in two separate answers, we would have answer of negative 5 plus I square roots of 7 over 2 and negative 5 minus I square roots of 7 over 2. Which of course you could break that apart a little bit if you wanted to and make that negative 5 halves plus the square root of 7 over 2 times I and negative 5 halves minus the square root of 7 over 2 times I. Now one thing you want to be careful about is when you're typing these in, make sure you don't accidentally put the I underneath the radical. It will never be underneath the radical. Okay, the I will always be outside. Sometimes I put it in front of, just so I can tell that it's not underneath. But pay attention to how they ask you to write your answers. It's not for me personally, but it depends on how they ask you to leave your answers. Sometimes they'll ask you one way, sometimes another. Let me pull one up real quick right here and specify. Yeah, so they probably typically like it this way, don't they? Yeah, if I'm grading it, actually I don't mind any of those three, but yeah, it can be frustrating if you don't type it in correctly, and so be careful about how they ask you. And so most of the time you say it'll probably be like this. All right. So if we have time, we'll come back and do this example 7. But as I said, I really wanted to get to do a word problem, so I'm going to zoom in here just a little bit. Okay, so this is one of something that's similar to one of the homework problems that you have. It says we have an open box that's made by taking a 30 centimeter by 80 centimeter piece of tin and cutting a square from each corner and folding up the edges. The area of the resulting base is 1400 centimeters. What is the length of the sides of the squares that we cut out? Okay, so we start with something that's 80 by 30, and then we're going to cut out little squares whose sides are length x. So when we cut those out, we end up with a piece of tin that, well, I'm not very good at drawing this today, apparently, but it's like, kind of like this. So we fold this side up and this side up, and then we get this. Well, if this started out being 80 centimeters, and I cut x centimeters off this end and x centimeters off this end, then this resulting side would be 80 minus 2 of those x's. And that would be this length right here. Does that make sense? Okay, now here I started out with 30 centimeters and I cut x off this side and I cut x off this side. So this would be a 30 minus 2x, or that's going to be the width of that side of the box. Now what we know is the area of the bottom of the box is 1400 square centimeters. That bottom of the box is a rectangle. How do you find the area of a rectangle? You take the length times the width. So our area is 1400 square centimeters, and that will be the length of the box times the width of the box. So we have a quadratic equation, but it's not yet in the form that we can use to solve it. So I'm going to need to simplify this quadratic equation. So I'm going to multiply it out. Now let me stop here just for a second. Why could I not just set 80 minus 2x equal to 1400 and 30 minus 2x equal to 1400? I'm sorry, because it's what? Not quite what I'm looking for. I may not have asked that question very well. When we solve using factoring, we have to have what on this side? Well, this part is already factored, but to set, yeah, I'm sorry, I wasn't asking my question very well, y'all. But to set, if you want to solve using factoring, what you have to have on one side is a 0. That's why I couldn't just set each factor equal to that 1400, because it's not a 0. So I'm going to go ahead and multiply through here. 80 times 30 is what? 2400. 2x times 80 is minus 160x. 2x times 30 is a 60x. And 2x times 2x is 4x squared. So we have 4x squared minus 160 minus 60 is minus 220x plus 2400 is equal to 1400. Now, if I'm going to use either factoring or the quadratic formula, I need to move this 1400 over here and make that a 0. So I'm subtracting 1400 from both sides, so I would have 1000. Now, fun fact, remember, if we want to, we could divide through by a number on both sides of this equation to make my numbers a little bit smaller. So if I divided everything through by 4, I would get 0 is equal to x squared minus what? 220 divided by 4. That will go in there, won't it? Yeah, it'll go in 55 times. Plus 1000 divided by 4 is 250. Okay. Now, we can try to factor this, or we could try to use the quadratic formula on it. What do you guys want to do? You want to try the quadratic? Is that what you guys said? Okay. So if we use the quadratic formula on it, A is 1, B is negative 55, and C is 250. So we will have x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So I have 55 plus or minus 2025 underneath the square root. Oh, I'm sorry. I moved it too far down, didn't I? All over 2. So that is, and it just about out of room, that would be 55 plus or minus the square root of 2025 is 45, and I just took that on my calculator, divided by 2. So we would have 55 plus 45 divided by 2, or we would have 55 minus 45 divided by 2. 55 plus 45 is 100 divided by 2 is 50. 55 minus 45 is 10 divided by 2 is 5. So do I really have 2 correct answers? Well, think about this. If x is 50, that would mean I would be cutting 2 squares of length 50. So I would have to have at least 100 units to cut from. 50 is too big for the setup. So while it is a solution to the quadratic equation, it's not a solution in the physical sense of the setup of this problem. So our x's would have to be 5 units long, or 5 centimeters long. Okay? And so the sides of the squares would be 5 centimeters each, because the other option, that 50, is too big for the lengths of the sides that we had to start. But on all of the word problems in this section, you'll end up with a quadratic function or a quadratic equation that you need to solve. Just remember, if you're solving it, you can put it in standard form, ax squared plus bx plus c, and use the quadratic formula on it anytime you want. Questions? All right, so starting on Wednesday, we will look at the graphs of quadratic functions, and we'll move on from there. So for Wednesday, you want to do section 7.4 for your homework. Okay, let me know if you have any questions. And oh, go ahead, I'm sorry. Yes. And let me know if you have questions, and otherwise I will see you then. Have a good day. Bye-bye.